my understanding of this time is that I've only got about a half an hour to talk. So normally I would want to go around the room and hear who you all are and where you're from, but I think we'll be able to do that later this evening. So I'll just kind of jump into it. I'll do a real quick, and I hope to be as interactive as possible. This is one of these things where, you know, the in-class experience is always much easier to do that with. But so I am what I call a physical glaciologist, which means that my training is in geophysics, and I apply geophysical principles to what I think of as physical process on ice sheets and glaciers. So I think you've heard from geochemists and climatologists, but I think my role here is to talk about like actual ice physics and how the ice sheets are physically changing. And so to get the ball rolling, or to start with, is a good start would be to say, okay, well, we have to define what qualifies as a glacier in the first place. So I'm gonna share screen here and give you some slides. Can you guys see my screen, I hope?
Yeah.
Great. So first off, what is a glacier? And this is a great moment since I can't see the whole participant list. And I don't know if you guys have been doing this already, but anybody want to shout out anything that helps them define what a glacier is?
Semi-permanent ice. Annotate tools too. If you want to use that sometime. Yeah, go ahead.
Sorry, say that again, Louise.
I was just saying they do know how to annotate the slides if you want to do that, but they also can just shout out.
Oh, wow. Could they annotate, like type in some answers in there? That's a neat idea.
It is a land-based ice.
Okay, so land-based ice, that's a good start. And what else?
A river of ice.
A river of ice. Ice made from piling up. Oh, I love this. Stream of ice, that land, year-round ice, semi-permanent, moving. Okay, I really like that last piece, that moving piece. So this is one of the massive moving ice. This is even better. It's like a word cloud. Louise, this is great. I've never actually got this. Moves under its own weight. That's like one of the things that always helps me feel like I've really defined a glacier. Is that once this pile of ice is moving under its own weight, then we really consider it a glacier. It's like a word cloud. I wish I had started doing this with my class earlier. So let's just sort of go through the fundamentals of how a glacier works. I guess do I have to ask you to remove your annotations, or can I do that?
You can.
I got it. Yeah, I got it.
Yeah.
Cool. So fundamentally, this is a cross-section of sort of a prototypical valley glacier. And so what happens is glaciers form in areas where snow falls, and glaciers form in areas where not all of the snow that falls in any given season melts. And this means two possible different things. One, you could have a tiny amount of snow or just a little bit of snow, but the summers are still cold, and so they're cold enough that not all of that snow melts. Another possibility is you've got warm summers, but in the winter so much snow piles up that not all of it is able to melt. And so over time, you get that snow piling up. You get that snow piling up. I have a feeling that at least somebody else of the speakers in the last day or two have talked about snow piling up so as to use that for ice cores for paleoclimate. What that means to me as a physical glaciologist is that as that snow piles up, it places a greater load, a greater overburden on the layers underneath, and then that snow starts to compact. And once it compacts up to the density of glacier ice, which is around 917 kilograms per cubic meter, which note, of course, that is a lower density than the density of water, so that's why ice floats, which is one of the things that makes ice a cool and different material than most things. Once it compacts into that density of ice, it begins to flow, and it's going to flow downhill. Flows as some would call it a viscoplastic fluid. We'll talk a little bit more about that in a second. But the question always comes up, okay, how far downhill is it going to flow? Well, one of the things that you may have heard about in some of the climatology discussion is that, have you guys heard the concept of lapse rate?
No.
Okay, Louise is shaking her head. So lapse rate is the change in temperature with elevation. So as you go up in the atmosphere, it's getting cooler. And this is happening because there's a lower density of air there. And so the atmospheric lapse rate is usually around 6 degrees per 1,000 meters, 6 degrees Kelvin per 1,000 meters. So if the ice is flowing downhill, it's flowing down this lapse rate and down into a region of warmer climate. So the ice is going to flow downhill to a point where there is enough melt down at the bottom here, so that there's enough melt that all the ice that flows into that area is going to be melting. And that's what's referred to as, or not all of it, some of the ice that flows into that area is melting. And that's referred to as the ablation area. So we've got up above, we've got the accumulation area, and that's where there's more snow, more snowfall than can melt. And down below, we've got the ablation area, and that's where there's more melting than there is ice flowing in from upstream to replace it. So that's these two different zones. And dividing these two zones is what we call the equilibrium line. And that equilibrium line, as you can imagine, because the lapse rate varies, or the lapse rate is pretty consistent, the temperature varies just about linearly as you go down this glacier. And so there will be a point where less snow survives, less snow survives, less snow survives, less snow survives. Finally, all of the snow that falls in any given year has melted by the end of the summer. And then as you keep on going farther down, you might find that there's snow on the ice at the end of winter, but all of that snow melts, and then a little bit of the underlying ice melts as well. All the snow melts, more of the underlying ice melts, until you get to a place where every bit of ice that moves down into this area is melted by the end of the summer. Does that make sense? Louise, if you can see all the participants, you can just go like this, or if people are nodding, because I can't actually see. Are there questions on this at the moment already? No questions so far. So the equilibrium line then, it's really tempting to draw this equilibrium line like this as a vertical line through the glacier. And in fact, I got this image online, and so it's got this vertical line here. But really, that equilibrium line should be drawn horizontally. Because, and this will come into another piece of terminology, because the best way to characterize this equilibrium line is not by its position in this direction along the glacier, but rather by its position in elevation. And so we usually refer to the equilibrium line on a glacier as the equilibrium line altitude, or ELA. So you might have heard reference to ELAs and people talking about, like, Meredith Kelly can determine what the ELA was of a glacier if she knows something about its the moraines that were left behind from it.
Dr. Hawley.
Yes, go ahead.
Can I ask a question?
Yes, please.
I remember watching this video where the ice in the middle, was it the snow or I can't remember, the ice was moving below from the surface. Something was moving in between, and when the top, the move from the top was different than in the middle. Is it like something possible like that?
So the differential motion is, and I think what you're talking about is like, so if I've got, let's see if I can draw this right. I've got the ice flowing here, it's flowing down at a certain rate. As you get shallower, it's flowing down at a faster rate. Is that the kind of thing you're referring to?
Right. Like there were like all kinds of move, but the layers were moving at this. We did it for one of the school of ice. I can't remember. This was before.
Okay.
And it was like, and then it was causing very unstable, conditions like the move was going. But anyway, I wasn't sure, like, wasn't it supposed to move at the same rate? Like, I was like amazed to see how the difference was measured. So
Yeah, that's a great question. And what I think I'm going to do is, in a second, I'll get into exactly what are the different mechanisms for glacier motion, and hopefully this will be answered then, if that sounds all right.
And Bob, tonight we can explore some of that with the glacier goo too.
Yeah, absolutely. That sounds great. That sounds great. So yeah, so the next question, I guess, that always comes up is, how is it that ice deforms and how does it behave? And the thing that's weird about glacier ice is that we usually think of, whenever we think of ice, usually when I think of ice, I think of an ice cube that I get out of the freezer. And ice that's of the scale of an ice cube and the sort of times we think of ice cubes, like how long does an ice cube stay an ice cube when you take it out of your freezer? Well, not very long, because you're usually taking out of this frozen environment and putting it into a much warmer environment, so it's going to melt, or you're going to drop it and it's going to break, or you're going to put it in a drink and that's going to melt it. But ice in a glacier, because first off, it is generally cold enough to stay frozen. Second, it's also thick enough that there's a lot of pressure under it, and so that that causes changes to the way it behaves. And third, it is deforming on much longer time scales than anything we think of in sort of the regular everyday world. And so ice is one of these weird materials that deforms. We talk about the deformation, or how a material responds to a stress. It's the word rheology. And the rheology of ice displays all three of the key rheological parameters that we usually define in engineering. And the first is elastic. So in an elastic response, this is all the difference, but this is all how we talk about rheology as how a material responds to stress. And stress, we define, it's like a pushing. So stress is how you're pushing on it, and strain is how it's responding. So rheology is how the stress gives rise to a strain. So ice has elastic response. It'll also undergo brittle fracture, and it'll also undergo viscoplastic response. And so I'll talk about these in a little bit more detail. The elastic response is, hopefully, at least at some point during your life, you have tried to get a piece of ice out of the ice bucket in your freezer and accidentally dropped it on the floor. And usually one of two things happens when a piece of ice drops on the floor. One, you get that brittle fracture. Almost always, there's at least a little bit of that. And that's just the ice breaking apart. But the other is, and I don't know if you've noticed this, and one of these things, it might be that you have to be a geophysics geek to really notice it, but I've often found that in addition to breaking, often that ice will bounce. In order to bounce, any material has to have some elastic response. And what's happening is the molecular structure is flexing, but it's not breaking, and it's not actually deforming. And in an elastic response, that means that it will flex, and then once the stress is removed, it will go back to its original shape. And as a glaciologist, I always carry silly putty with me. So I'm going to sort of demonstrate these three rheological responses. And so the first simple one is elastic response. I've got the silly putty, and I can show you this elastic response by just bouncing it off my desk. And now we're going to see whether I can look at the camera and look at the screen and be able to catch it all at the same time. It's kind of like juggling. So there we go. So that's bouncing, and that's this elastic response. The second one is a little bit harder to demonstrate with silly putty, but it's still possible. And that is brittle fracture. And what's interesting about this brittle fracture, usually when I do this as a classroom demo, I bring in a hammer, and you can actually shatter silly putty even at regular room temperature with a hammer. What's interesting is I usually do that in a normal air-conditioned temperature classroom. And so I tried that earlier today, but in my office and my house, it's a lot warmer. And because the temperature has a very strong effect on the rheology, shattering it with the hammer was not possible. But I'm going to show you, if you've never seen silly putty break, all you have to do is you have to strain it at a very high rate. So you have to pull it really fast. So you have to go, oh, that still didn't work. And it's like, it's because it's so warm. Like, there we go. So I've just broken the silly putty. And there's this like nice little fracture plane there. It may be the first time you've seen silly putty broken, but it is one of those things that happens. And so that's something that you also see in glaciers. You'll see brittle fracture in glaciers, and that's how you get crevasses. Then the last thing you find at very low strain rates and very long time scales is viscoplastic response. And so what I'm going to do to see if I can demonstrate this is I'm going to put this silly putty on the edge of my other desktop. I wonder if I can do that without de-sharing the screen. Can't. Well, hang on just a second. I'll just show you this, show you what I'm doing. Got another camera to show my other desk. And we're going to put this silly putty right on the edge. And if it disforms viscoplastically or viscously in the time that I'm talking to you, it will be starting to drip off that edge. And so if I forget, try to remind me that, hey, we want to see what that looks like. Usually I'll just put it off to the side. So let's go back to these slides. So those are our three main ways that ice deforms. So let's talk a little bit about this question of how ice is moving down the glacier or moving down slope. And so for that, I'm just going to just give you a little bit of a sort of draw the same kind of thing that I had diagrammed before, but it's going to be a little bit more straightforward. So in this case, we've got the accumulation zone here and the ablation zone here. And then you would find the ELA somewhere in the middle. There were some lines in initial drawing that you guys saw. You had ice flowing in this direction, but they were very detailed. So this as a diagram, I want to talk a little bit about how this ice is moving downhill. And there's two key ways that the ice is going to move downhill. One is sliding. And with basal sliding, I'm just going to write basal. With basal sliding, you've just simply, it's almost as simple as just saying, okay, well, it's just this ice sitting on a piece of rock or a piece of deformable sediment, and it's just sliding along its substrate. I say it's simple, but that actually turns out to be a fairly difficult problem to understand from a physics standpoint. And so in basal sliding, all of the ice is deforming, or rather all of the ice is flowing at the same speed. Right? Because you've got the ice is all flowing based on this, it's just sliding down the hill. Now, there's also another mechanism by which this ice is moving, and that's internal deformation. Internal deformation. And this internal deformation comes from this viscous response to stress. Now, internal deformation gives rise to a much different flow profile. And a way I'm gonna draw an internal deformation profile upstream a little bit. Actually, you know what? I'm gonna blow this away and draw it again. And so what I'm going to do is I'm going to draw the sliding. And then I will draw the velocity due to internal deformation just a little bit downstream. And so the reason for this change is that the internal deformation velocity depends on the shear stress, and the shear stress depends on how far down in this glacier you are. The deeper you are in the glacier, the greater the shear stress. And so that deformation velocity looks more like this. So you can kind of see now that the velocity due to internal deformation is greatest at the surface and smallest close to the bed. So the entire velocity is this combination of the sliding velocity plus the internal deformation velocity. So hopefully that makes sense in terms of just the distribution of velocities with depth in the glacier.
Sliding velocity will be more with depth?
Sliding velocity should be the same. That's this one on this side. So that's uniform with depth. And one way to think about it is the very bottom part of the ice is just sliding along relative to the bed, and the other parts, like up above, these other layers, are simply riding along on top. It's just like a flatbed truck, and you're riding along. Now, with internal deformation, each bit of ice is moving relative to each other bit of ice. And so as you get deeper and deeper, this curve, this curve right here, gets steeper and steeper because that shear stress is greater and greater. But also because, as with the sliding, each piece of ice is riding on top of something underneath it. When you get to the very top, this is the accumulation of all of those different strains due to viscous flow. And so that varies. So I'm gonna write here deformation. And right here, slide.
So there are also lateral differences in flow, right?
Absolutely, and I'm glad that you mentioned that because that's what I'm going to go for next. So now we're going to look an eagle eye view down at a glacier. And so as a geophysicist, I always like to think of the simplest shaped glacier I can come up with. And so here we're just going to have one that's just flowing downslope in this direction. And so I guess I'll ask the question of the group. If you thought I've got part A, part B, and part C of the glacier, which of these 3 points do you think would be most likely to be going the fastest?
E.
Okay, I have
A and C?
I have one for A and C. I have one for B. We got everything. That's great. B, okay, I've got another B. Does anybody want to, oh, that's right, you can annotate. Does anybody want to explain why they think what they think?
I think the lateral sliding, what to say, this, if the glacier is flowing through the valley, I think the sides will move or there will be, I mean, it's just coming as a logical thing. I don't know, maybe.
Oh, B, there's less friction.
Yeah, A and C will have more friction, so we'll move fast.
Okay, so yeah, in this case, A and C have closer coupling to this valley wall. And so they actually do have a little more friction. And so you're going to see a profile that will look more like this. And so that profile it's kind of curved. I've drawn it more like a V, but it's really more like a U. So you get faster flow right in the center. And one way of thinking about that is that there may be sliding right here at this valley wall, but this part B is far enough from that sliding that it's getting the benefit of the sliding, but also not seeing the drag of the sliding area as much. It's very, very similar to what you see in the vertical sense with it going to this.
Oh, okay.
Yeah.
So B will move faster.
So B will move the fastest. Yeah, absolutely.
Okay.
So, yep. And then another sort of the last one that I usually do is let's go from top to bottom. So if we've got A, B, and C here, and now we'll say that, let's say that B, this is at the ELA, A is in the accumulation, and C is in the ablation. And so again, this is a huge generalization because we've now put together this rectangular glacier, and we're going to say everything else is equal. So the question, I guess, is faster at A, faster at B, faster at C. I see one heart in B. I see a star near B. I see one heart at A. Do I have anybody going for C? I love this because it's almost like democracy. Like we can vote for just about anything. Okay, so does anybody who chose A want to sort of talk about why they chose A?
I think because it has less gravity or less friction, and because it's more accumulated, it's less packed.
Okay, right. So this is in the accumulation area, and so you've got some fern, you've got some snow. Let me just draw a sort of a side view on the same thing. So we would have A and then B and then C. Okay. What about B? Who thought about B?
B seems like it would have the steepest slope and then also more compacted ice from above.
Okay.
I think it's kind of influenced by both the weight of A and the melting of C, so it's got the most movement, something like that.
Okay. Yeah, well, so this is an interesting way of thinking about it. So again, this is a gross overgeneralization. But one way of thinking about it is that as you go down from the accumulation to the equilibrium line, and then as you further go down from the equilibrium line into the ablation zone, every moment or every year, let's say that each year we go farther, we go 1/5 of the way between the accumulation area and the equilibrium line. So in year 2, we're here, in year 3, we're here, in year 4, we're here. One of the things that you find is that after you've gone from this spot to this spot, you've got all of the same material that you had in the first spot, in this spot, but now you've also had more snow accumulate onto you. And so in order to maintain this steady profile here, you're going to have to push more ice down this way, more ice, until you get to the ELA. And once you start to have some ablation, you're going to be pushing less ice and less ice until you to the very bottom of the glacier to get the toe, at which point there is no, you don't need to push ice forward at all because all of the ice that's come into this spot is melting in any given season. And so what it turns out then is your profile looks more like this, is that it's slowest at A and gets to be fastest and generally thickest at B, and then it slows down towards the accumulator or towards the ablation zone. So we've kind of put together a little bit of intuition about how ice is moving both in the vertical profile and the horizontal across the glacier profile and in the along glacier profile. So this is ask away.
So given just this one and then your obviously your previous ones, in broad brushstrokes, when I think of looking at a glacier, you see more of the crevices. I mean, the crevices obviously continue down to the bottom, but it seems like they're made in that middle zone, which if I'm adding up your 3 versions, the middle is going to move the fastest and it's going to silly putty and snap and get more cracks. Is that?
Yeah.
A plus B plus
exactly
B.
Right. Yeah, that is exactly right. So there's 2 pieces of it, I guess. And one to remember is that this velocity is a combination of both sliding and internal deformation. And then the other thing is that the reason that ice behaves in a brittle, it's actually the technical term for the rheology is plastic, which is kind of hard because a lot of people think of plastic as being deformable. But when ice behaves in that brittle way, it's because it's being strained faster than it can sustain. And so it's in these places where it's not just that the velocity is fast, but also the velocity is changing quickly. And that tends to happen right around the ELA oftentimes. The other thing that can sometimes happen to generate these crevasses is, let's say, let's see, I'm just going to come up with a new drawing. Let's say the ice comes down this way. Well, if or the bed comes down that way, the ice has to come down this way. As it's going around this corner, it's going to be forced to bend. And so it might bend too fast. And so you end up getting these cracks right along there. If that makes sense. So that's your crevassing. So realizing that there was no way that it would actually come through all of this material in the time I've got, one of the things that I thought I would do is give you guys a little some options. So here are some fundamental options for what we can work on next. So the most basic and important information about a glacier is its mass balance, so how much is gained versus how much is lost, and that's something I've done quite a bit of research in. The other thing that we could work on is sort of the discussion between, ice sheets and sea level, how ice sheets and sea level are combined. We can also talk a little bit about more current events in ice sheets. So I know that Thwaites Glacier was one of the things that was advertised in my discussion. And then I talked a little bit about small glaciers at the very end. But I kind of feel like, especially given the time we've got, we need to determine whether we want to talk about mass balance or whether we want to talk more about sort of current events in ice sheets and sea level. Does anybody want to vote? You guys could vote with your stars if you want, right over here on this column. And Louise, also let me know when, I see one for current events, that's good. I don't want to go too much over, right? Do we have like 10 minutes left? So you're muted still.
There we go. Why don't we go about 10 more minutes? That'd be great.
Okay. So ice sheets and sea level, current events. Okay. That's beautiful. And so I will skip over this sort of types of glaciers and mass balance. And the types of glaciers are things that you guys can look at in the slides. Those are in the Google Drive, so you can always look at that. So let's go on and move to some sea level and current events. And the sea level thing can really be summed up by a figure like this. Let me just clear these annotations. So fundamentally, this is all, ice sheets and glaciers are part of what we refer to as the water cycle. So the water cycle in which you've got storage in the ocean, you've got storage on land ice, you've got storage in clouds. You've also got a small amount of storage as fresh water in rivers and lakes. But fundamentally, the water cycle is all about moving water from and to and from these different reservoirs. And so one of the ways of thinking about it is the ocean's a great big reservoir of water. This is just the Antarctic ice sheet, but Greenland is also part of that. I'm gonna write Antarctica and Greenland. And you can imagine the change in sea level in a steady state environment. And by steady state, I mean where glaciers and ice sheets aren't changing and where sea level is not changing. You still have this cycle, right? You've got evaporation off the oceans, deposition onto the glaciers, you've got melting off of the glaciers and going into the oceans. And so there's two ways to think about this sea level question. And one is think about the size of this reservoir. So the size of the reservoir is important because that's where we get numbers like if the entire Antarctic ice sheet were to melt, it could raise sea level by 50 meters. That's a huge number. However, the other thing that's important, and so the other glaciers, this is like little glaciers and ice caps around the world. The other thing to remember, and if they were to all melt, the sea level rise would be much, much smaller. But the other thing to remember is it's about not only the size of the reservoir, but also how far open this tap is. And so the contribution of different glaciers to sea level rise is not necessarily, to current sea level rise, is not necessarily related to the volume of water they could contribute in total. And right now, in fact, other glaciers and ice caps are contributing more to current sea level rise than the Antarctic is. Because currently the East Antarctic ice sheet has a slightly negative mass balance, but its current contribution to sea level rise, it's the tap, if you will, is not on very hard at all. Greenland and small glaciers and ice caps are contributing a significant amount more. So if you think about paleo ice sheets, hopefully you've all seen or heard from, Louise, you could just give me a thumbs up if Meredith has already talked today. Great. So hopefully you've talked with Meredith and heard from her about the Laurentide ice sheet. So this is a great big ice sheet that, based on research from people like Meredith, who can look at these former lines along where the ice sheets have been, they can determine something about the volume. We are pretty confident that sea level was several tens of meters lower during the last glacial maximum, during the last big ice age. So this is an example of what the coastline of Florida would have looked like with that kind of sea level lowering. Now, if we look at the kind of sea level rise we might expect with say, for example, if the entire Greenland ice sheet were to melt, that can also impact coastlines, and that's this other coastline we have down here. And so the key thing I think about sea level, and I think I'm not the best person to talk about how sea level changes coastlines, but the key thing to remember about all of this is that a small change in the vertical, because that slope is very, very shallow, can result in a pretty big change in the horizontal. And one way of calculating it is people like to live near the water. And so people are always near the coasts. And so you could Google lots of different visualizations of it. They're very useful. So I promised to talk about Thwaites Glacier, and Thwaites is, I'll do a little bit of Antarctic geography. I don't want to go too long, and I apologize, Louise, for this going so long. But so here we've got the Antarctic, and this is just a plot of the various flow velocities. And so just some of the geography that you'll hear, this is the West Antarctic ice sheet. This is the East Antarctic ice sheet. And so just generally speaking, they are transected by the Transantarctic Mountains, which go between them. And you'll see sometimes you'll hear talk about the Antarctic Peninsula. In addition to that, you'll hear talk about the Ross Ice Shelf, which is this guy right here, and the Filchner-Ronne Ice Shelf, which is this guy right here. These ice shelves are very important because they're floating ice. They are ice which has been, which is formed on land and then flowed off and is now afloat. And the trick to the floating ice is this: it is already afloat, and therefore it's already displacing its total mass in sea level. So any contribution to sea level that ice was going to have specifically from itself, it's already made. Once it melts, it will be the same volume as the water that it had displaced already. The difference is, if you were to remove, say, this chunk of ice, then these ice streams, the ice flowing into the Ross Ice Shelf, ends up accelerating, because right now that's providing what's referred to as a buttressing effect. So it's a little bit like a cork. Or as I was emailing to Louise earlier today, let's say you're the ice and you're sitting in a wheelchair and somebody's pushing you down the hall. You're pushing out against the walls with your hands to try and stop this person from pushing you down the hall. And when you lose that buttressing, when you don't have that wall anymore, this person can just shove you and you're going to roll straight down the hall without any stopping. So the place that everybody's talking about right now is the Thwaites Glacier area, and that's this area right in here. And it becomes really, really important because it's a place, it's hard to see on this scale, but there's really, really fast flow right here in Thwaites. And in addition to there being fast flow, the ice is in contact with the water right there. So that is, that's this area right here. And I'm just going to zoom in on the Thwaites Glacier area. So like I said, it's right there. You've got and when we talk about these different glaciers, really they are more like ice streams. In other words, all of this here is ice moving towards the sea. But the fast flow is all concentrated in these, boy, it's tough to find a good, there we go, good color with these color maps. The fast flow is concentrated in these little ice streams. And that's largely because of what's happening at the bed. So what's at the bed is some deformable sediment. Probably under here, it's hard rock, and so it doesn't slide nearly as easily. What's really important, especially in the Thwaites Glacier area, is the grounding line. And so that is the line where the ice is going afloat. Once it goes afloat, it no longer has, you could imagine, to keep going with that wheelchair going down the hall analogy, grounded ice, you could have your feet down on the ground and you're dragging them along the floor of the hall. But once that ice goes afloat, you have to pick up your feet and you lose that friction at the bed. And so the water doesn't give you any back pressure at all. And so one of the things that we're looking at especially is how this grounding line, no, that color doesn't work there, how this grounding line is changing and how it might retreat as the ice thins. So that's kind of the really big, the big picture discussion. And unfortunately, I have to report that because of the pandemic, which is keeping us all on Zoom today, a lot of the current expeditions, so there's a big multinational effort to try and understand more about this Thwaites Pine Island region, but pretty much all of those have had to stop their field seasons for this season. But what I wanted to say about it was that this is one of these things, it's definitely an idea which really has come of age. The first in the literature that I can find, people talking about how the Pine Island Glacier, Thwaites Glacier region are an important component, came from 1980. This guy, Terry Hughes, who was at the University of Maine, pointed this out a long, long time ago. And so it's actually taken us until the last 5 years to really start digging into it. So I realize I feel like I'm just about at time, and I want to respect. I know that you guys have been on Zoom forever, so I don't want to go too far over. I'll stop the share so I can see people. You know, do we have time for a couple of questions, Louise, or should we just break now and come back and talk later?
Does anybody have a burning question? Because Bob's going to be back in a little bit, and we want you to have a nice big break so you can stretch and eat and all that kind of stuff.
How's the silly putty doing?
Oh, thank you for asking. Yeah, it is definitely starting to drip off. So here we go. I don't know if you can see it that well, but you see there's this little droop starting. And so what I would recommend, if you have silly putty available to you, just like let it sit for a while and just watch as it just goes.
We have silly putty.
Yeah.
We just made a giant bag.
Oh, right. Yeah, that's right. You made the oobleck or the glacier glue or the flubber.
We'll play with that in a little while and talk about how the glacier moves from the top, the bottom, the sides like you did, and how you can explore that with your students with the glacier group. So,
that's great.